So let's talk a little bit more about limiting reactant and specifically how we use it in the theoretical yield. Now, we need to know what is limiting because we need to know how much we can produce. Okay, once the limiting reactant has been determined, you can determine the maximum amount of product that can be produced. That is the definition of your theoretical yield. It is the maximum amount of product that can be produced. Now, we cannot produce any more than the limiting reactant lets us. So that's why we have to figure out what the limiting reactant is. We figure out what limits the reaction, and then we're able to calculate the theoretical yield. Okay? Every atom of the reactant reacts with another until one runs out. Okay? The one that runs out is the limiting reactant. And the theoretical yield is the mass of everything that's reacted. Okay? It's the mass of everything that's produced. Okay, so let's look at how we do this. So this first step up here should look very familiar because that's how we figure out what the limiting reactant is. And this is how many moles that can be used. That's how many moles of that oxygen that are available to be used in the reaction. So when we're looking at this, this is how many moles are in the reaction. We can plug that in here, and then, well, in one reaction, you can figure out any product. So in one reaction, you have 4 moles of your nitrogen monoxide, and you have 6 moles of your water. So you can convert it, now that you know how many moles are in the reaction, or that value, then you can convert it to your product. Okay, so let's look at this example B1. It says a student is responsible for precipitating out lead from a solution to dispose of it in an environmentally responsible manner. The student has 200 grams of lead 2 nitrate and 140 grams of potassium iodide. It says, what is the mass of the lead iodide expected to precipitate out of the solution? So first thing we have to do is write our balanced chemical equation. So our two reactants, we have our lead nitrate, lead 2 nitrate, so Pb, which has a positive 2 charge, and then nitrate NO3, the negative 1 charge, and we crisscross, and we get our first reactant, which is PbNO3 2. So we'll write that down. We get PbNO3 2. Okay, our next reactant that we have is 140 grams of potassium iodide. So it's just potassium, which is a positive 1 charge, iodine, negative 1 charge, and we crisscross and we get Ki. So that's our other reactant. Okay, so plus our potassium iodide. Okay, now in this product, what we'll see is produced, it's a precipitation reaction, so we have a double replacement reaction. So lead will be bonded to iodine and potassium will be bonded to nitrate. Okay, so lead having its +2 oxidation number, it'll have PbI2 plus our potassium, which is KNO3, because they both had a 1 charge, basically positive 1, negative 1. So here's our chemical equation. Now all we have to do is we have to balance it. So when we're looking at this, the only thing that's really not balanced are our potassiums, or sorry, our nitrates and our iodine. So to do that, we need a 2 right here and a 2 right here, and that gives us our nice balanced chemical equation, and we can start working everything out from there. So we'll start with basically what we have in the beginning, the 200 grams of lead 2 nitrate. So we'll start there, 200 grams of lead 2 nitrate. Okay, now we need to get it from grams to moles, so we have to have the molar mass of our lead 2 nitrate, which is right around 331 grams per mole. That converted it to moles, and then we look at our reaction, and in a reaction, lead 2 nitrate, we just have 1 mole in a reaction, so it's just 1 mole in one reaction. Okay, and work all that out, and that will give us a value of something right around 0.604. Okay, that's what we have in our reaction for our lead to nitrate. Okay, so let's see, we're starting with 140 grams. We'll just move this up here and leave right there. 140 grams of our potassium iodide, and we'll see if this is less, and if so, then it's our limiting. If it's more, then it's our excess. So 140, we need the molar mass of potassium iodide, which is 166 grams of potassium iodide in 1 mole. And in our reaction, we see that there's 2 moles in our reaction, so 2 moles in 1 reaction. And we see that it produces right around 0.422 in a reaction. So this is obviously less, so therefore this is our limiting reactant. So that's what we're going to start with when we're trying to find our product. So we don't even need this portion right here, because all we're looking at is just the product produced. So that 0.422, that's what we're going to start when we're trying to find the mass of our product. So we'll start with that number. Kind of move the rest of this out of the way, and we'll start with this number. Okay, so we're trying to start with that 0.422 in a reaction, and we're trying to figure out how much of our lead iodide is going to be produced. So in a reaction, so in one reaction, we have 1 mole of lead iodide, lead 2 iodide. Okay, and then all we have to do is just get it into grams. So 1 mole of lead 2 iodide has a molar mass of 461.01 grams, which we multiply that out, 0.42 times 1 times 461.01, we get 194.55 grams, and that's the theoretical yield of our potassium iodide. Okay, let's go ahead and look at example B2. It says a student is responsible for extracting copper from copper 2 sulfate in a recycling plant. The student mixes 50 grams. So we have 50 grams of copper sulfate with 500 grams of zinc in an aqueous solution according to the chemical equations shown below. What is the expected? We're looking for the theoretical yield in grams of copper or solid copper to be extracted from the solution. So let's go ahead and work this one out. It's already given us a nice balanced chemical equation, so all we got to do is start with what it gives us. So we have 50 grams of our copper 2 sulfate, so CuSO4. Go ahead and set that up, and then the other reactant that we have is 500 grams of zinc, and set that up. Okay, so from here, all we have to go ahead and do is we're going to need the molar masses. So let's go ahead and we'll start with our copper 2 sulfate. So in our copper 2 sulfate, it has a molar mass right around 160. So 160 grams per 1 mole. Go ahead and set that up. And then in the reaction, we see that copper 2 sulfate is just 1 mole in 1 reaction. So we go ahead and work that out, and so basically it would just be 50 divided by 160, which is 0.3125 in a reaction. And then we have our zinc, which the molar mass of zinc is just 65 grams, right around there, give or take, and it's 1 mole. And then in a reaction, we see that 1 mole of zinc in 1 reaction, which we work that out and we'll get something right around 7.69 in a reaction, and so therefore that is much greater. So this zinc is our excess reactant, so we see that here is our limiting. So we can get rid of the zinc because we really don't need it in this problem, and let's go ahead and find our theoretical yield. So in looking at this, our theoretical yield, and we want to find it of solid copper. So it's a 1-to-1, and we'll start with our 0.3125 in a reaction. Okay, and one reaction has 1 mole of our copper, and then to take it from moles to grams, we just use our molar mass. So 1 mole, and we look at our copper, which is around 63.5 grams. Go ahead and multiply that out, and we should get something right around try that out, right around 19.84 grams of copper, and that would be our theoretical yield.